Hello dear students, welcome to Pen and Paper Chemistry on YouTube, and we are continuing with learning of the properties of aldehydes and ketones, and this is part 4 of the set of videos. What are you required to do? Yes, simple. Keep your pen, paper, notebook ready so that you can take down notes for offline reference, because you know that I share a lot of beautiful flowcharts with you which help to make chemistry easy and fun to learn. We've already dealt with part 1 of the properties, where I had given you this flowchart for nucleophilic addition and nucleophilic addition followed by elimination, and I also told you to keep a little space below it because we are going to add the next part of our flowchart to this, and that is what we are going to talk about today. That is reduction reactions of aldehydes and ketones. So your flowchart will look something like this. See over here? Yes, there is one more part to come, and that is the oxidation reactions, okay? And polymerization as well. So leave space for it. Okay, a bigger version of the reduction reactions of aldehydes and ketones. What are the various products formed when aldehydes and ketones are reduced using different reducing agents? So please make a note of this chart. For this class, just pause the video, draw a rough flow chart, or if you have felt pens, sketch pens and your ruler with you, please go ahead and draw it properly with colored pencils so that you are able to recall them easily. As always, I'll keep my flow chart on the right hand side top corner so that I can refer to it and write the reactions. Let's start with the first one. Aldehydes and ketones can be converted to alcohols by reduction using agents like sodium borohydride, which is a mild reducing agent, lithium aluminium hydride, which is a stronger reducing agent compared to sodium borohydride. We have already discussed this under alcohols. There can also be catalytic reduction possible using hydrogen gas in the presence of nickel or platinum or palladium. Aldehydes are reduced to primary alcohols and ketones are reduced to secondary alcohols. Remember, we have done these reactions as part of the preparation of alcohols. So go ahead. What happens over here is you've got a carbonyl compound, C double bond O. So when reduction takes place, electrons move and H becomes attached here and an H becomes attached here. So applying the same principles, H, C, H, double bond O, you've got methanol when it is reduced. Now for the reducing agents, just close your eyes, try recalling the reducing agents. Yes, I understand there is a bit of memorization done over here, but then we all can't help it, right? We have to do what we have to do. Go ahead. So H, H, C, OH and H. Can you tell me what product is this? Wonderful. This is methanol, CH3OH. Go ahead and write the product formed when ethanol is reduced. Again, close your eyes, try recalling the reducing agents. Same way, reduce propanone, CH3, C double bond O, CH3. What will be the product formed? Again, step by step, and then a lot of it becomes pretty easy. Go ahead, try writing the products yourself. You get an OH here and an OH here. So what product is this? Yes, Again, let's name it according to the IUPAC system 1, 2 and 3. Oh yes, this is propan-2-ol. Remember the IUPAC system of nomenclature which we've dealt with earlier. Okay, you want to check the product over here, CH3H, COH and H. What is this? This is ethanol, C2H5OH, ethanol. Better to write the name of the product so that you remember it. In other words, by using any of these reducing agents, we are able to convert aldehydes and ketones to alcohols. Let's move on to the next one. Now look at the flow chart. If we are converting aldehydes and ketones to alkanes by any of the three reducing reactions. So we've got Clementine reduction, we've got the Wolff-Kishner reduction, and the third one is using red phosphorus and HI at 150 degrees Celsius. All of these are giving you the product as alkane. What is the principle behind it? So you've got the carbonyl group, right? This carbonyl group is getting converted into CH2 group, right? So one oxygen is being replaced by 2 hydrogen by the process of reduction. Then what is the difference in the three of them? Of course, red phosphorus and HIs are standard reducing agents. Come to zinc amalgam and concentrated HCl. Look at the reaction conditions. Compare the two. Here this is in an acidic medium, whereas the second one is in an alkaline medium using ethane 1,2-diol or ethylene glycol. Both of these, where are we going to use? If I have an aldehyde which is sensitive to acid, then I am going to use Wolff-Kishner reduction. If I have an aldehyde or a ketone which is sensitive to alkali, then in that case I am going to use Clementine reduction. But in both the cases I am going to get the same product, that is alkane. In fact, in all the three cases our product will be alkane. So what do you have to do? In each of these reactions, you are simply going to convert the C double bond O to CH2 and write the name of the product. So, for example, I have HCOH. But, oh, look what we've got here. We've written that methanol does not undergo these reactions. So, do you think I can write the reaction with methanol? No, I cannot. So what do? I take another aldehyde. So I've got over here CH3CHO. Now what will be the product of this reaction? You can either use zinc amalgam. Amalgam is with mercury and concentrated HCl, or what is there in the Wolff-Kishner reduction? Wolff-Kishner reduction is when you treat it with hydrazine and then you treat it with KOH in the presence of ethylene glycol, that is ethane 1,2-diol. CH2, CH3 and H remain in place. So what is this product? Isn't it weird? No. I think let's start writing from here. So we have CH3, CH3. What is this product that I have got? Wonderful. I have got ethane here. So a carbonyl compound, that is an aldehyde, has been converted to an alkane by any of the three methods. Let us not forget the red phosphorus and HI as well, right? Now these reactions, the Clementine reduction, Wolff-Kishner reduction, these are named after scientists. So they are called as name reactions. So you could be asked, what do you mean by Clementine reduction depicted by means of an equation? So then you have to describe the whole thing, reducing an aldehyde or a ketone with zinc amalgam and concentrated HCl, to produce alkenes is known as Clementine reduction. What is the role of zinc amalgam in concentrated HCl? Yes, this is liberating hydrogen, the active hydrogen known as nascent hydrogen, which is going to reduce the carbonyl compound. So go ahead and write the product over here. We've done it just now. Let me change then let me give you another thing to write. CH3, C double bond O, because as we said, this reaction is applicable for aldehydes and ketones. So what product will you get over here? What do I replace the double bond O with? Yes, CH2, and the product would be propane. Got it? Well done. Okay. Now write the reaction for Wolff-Kishner reduction. So here, if you remember in the previous video, we've already done when carbonyl compounds react with ammonia derivatives. We've done a full video on this. How are you going to write? That's why I've put a question mark over here. Can you please complete it for me here? So I am going to flip this around. If you really want to test yourself, go ahead. Let's see how sincerely you've been doing and you've been following the videos that we've been doing and the topics that we've been doing so far. H2O, remember the box? Yes. So this was CH3, CH double bond N, NH2, right? And then the reduction of this particular carbon, that means now the nitrogen, it's not under heavy load, so it decides to move away and form N2, right? And CH3, CH. So because we are removing the double bond over here, we will get 2 hydrogen attached to it. So what is the product formed again? Yes, this is ethane. Remember, can I write this reaction with HCHO? No, I cannot. That is why in the flow chart also I have put it as an HCHO with a strike through it, right? Would you like to write the same reaction with CH3, C double bond O, CH3? I knew that you would guess that I'm going to give you this challenge, right? Go ahead, write the reaction. You could also, just write it as a skeletal equation. It's okay to write it that way. Skeletal equation means I can just mention that first I'm going to show the reaction with hydrazine, so NH2, and then I'm going to treat it with an alkali in the presence of glycol, and just write the final product over here, CH3, CH2. What does it give you? Well done, it gives you propane. All good so far? Reactions with red phosphorus and HI, 150 degrees Celsius. Please complete the reaction. That's for you to do. The next that we've got is Mpv reduction. M for Mervyn, Pondorf, Worley reduction. Please pardon my pronunciation if I have gone wrong anywhere. What is this Mpv reduction? It's basically a redox reaction. What is this reaction? Wherein what we do is we treat an aldehyde or a ketone with a secondary alcohol in the presence of aluminium alkoxide to give us an alcohol and a ketone. Oh, it's a complete mess, right? We don't know what we are talking. Okay, to make things simple, look at the colors that I've used over here. You are converting an aldehyde or a ketone to an alcohol in the presence of aluminium alkoxide and using a secondary alcohol. In the process, the secondary or alcohol gets converted into a ketone. Now, recall what we've done in reduction and oxidation. Converting an aldehyde or a ketone to alcohol, what would you call it as? What is this process? Yes, this is reduction, right? On the other hand, a secondary alcohol getting converted into a ketone, what is this? Yes, it's an oxidation reaction, right? So that's why I said it's basically a redox reaction, right? So reduction and oxidation are taking place. Now, instead of words, we actually have to deal with formulas, right? So we are going to go to that step by step. CH3CHO, that's the aldehyde we've taken. The secondary alcohol, isopropyl alcohol or propan-2-ol. The alkoxide that we are using over here is aluminium isopropyl oxide. Don't worry, this sounds like a big name, but we are going to break it down to make it simple. For now, just understand aluminium isopropyl oxide. As we said, our aldehyde is getting reduced. So what will be the product of reduction? CH3, CH, OH and H, right? This gives us an alcohol. And what about the secondary alcohol? It's undergoing oxidation. So our secondary alcohol is getting oxidized. Now oxidized means it's going to lose out the 2 hydrogen here, correct? So what will be formed here? CH3, CH3, C double bond O. Doesn't it sound simple now? Yes? Interestingly, this reaction is reversible. We'll talk about this a little later. For now, go ahead and complete this reaction. What will be the product of reduction of ketone and what will be the product of oxidation of this? So you're just adding hydrogen here and removing hydrogen from the second molecule. If you are unable to answer this, sincerely, I would advise you to go back to the topic of alcohols and revise it first in order to understand the difference between primary, secondary, tertiary alcohols. In fact, I've loaded a separate video wherein I've dealt with N, secondary, primary, iso, neo, all these terms have been dealt with 1 degree, 2 degree, 3 degree. I've explained it very, very clearly in those. So request you to go through those videos before you proceed. Otherwise, you won't actually enjoy this lesson. You may end up memorizing it, but then it will become very boring and burdensome. I'm waiting for you to write the reaction. Okay, written. So we have over here CH3, so I'm going to reduce it, CH and OH, and we have over here CH3, C double bond O. Okay, all good so far? Now coming to an interesting aspect of this particular reaction. What happens is the products on the right hand side can change back to the reactant. So I'm going to just make space to show that. In other words, you've got a reaction going in the forward direction. This reaction is reversible. In other words, my alcohol, secondary alcohol, actually gets oxidized right back to the ketone. And we've got a special name for this reaction, what is known as the Oppenauer oxidation. That means the secondary alcohol getting converted to the ketone, it is getting oxidized in the presence of again aluminium isopropyl oxide and on being heated. In order to keep things simple, I had not drawn the reversible arrow earlier so that you don't get confused. Right? Again, the reverse reaction is a redox reaction, but it is oxidation. So we are speaking in terms of aldehydes, right? We are dealing with the topic of aldehydes. So we are keeping these in mind. In the first, when we talked about reduction, the aldehyde was getting reduced to a primary alcohol. The ketone was getting reduced to a secondary alcohol. Up and out oxidation does take place with aldehydes. That means this is reversible, but the aldehyde form can actually undergo aldol condensation and so on, about which we have not spoken still. So that is why we don't prefer to carry out the reverse reaction. On the other hand, in the case of secondary alcohols, yes, they do get oxidized back to the ketone. Now, just now I said we avoid, right? We wouldn't prefer this reaction to go in the reverse direction, although yes, it is possible. It's a reversible reaction. So I can represent this generally as, so the carbonyl compound is getting converted into an alcohol and the secondary alcohol is getting converted into a ketone. This is called the Mpv reduction. The reverse is the Oppenauer oxidation, redox reaction. So as I said, if I want to obtain the secondary alcohol from the carbonyl compound, that is the aldehyde or the ketone, I want that this reaction should not come backwards. Now, recall the Le Chatelier's principle. What does it say? Any process in equilibrium, Le Chatelier's principle. I hope I'm getting the pronunciation correct because it's a French name, right? It says whenever you try to disturb a system in equilibrium, it will always try to oppose that change. You tell a student to study, he'll say, I'll not study. You tell somebody to go outside and play, like, I won't go and play. You'll tell somebody, okay, sleep now, it is very late. No, I won't sleep, right? So Le Chatelier's principle is something like that, opposite to. I want this reaction to proceed in the forward direction. What should I do? Recall what you've learned earlier. Yes, we remove one of the products, and since the ketones can be distilled off easily, we usually remove them from the reaction mixture, right? Second is, one of the reactants can be taken in a higher concentration. Now, my main guest of honor is the carbonyl compound and it's in limited amount. What can I take in unlimited amount? What can I take in excess in order to keep the reaction in the forward direction? Yes, I'm going to take the secondary alcohol over here in excess so that the reaction proceeds in the forward direction. How will the reaction proceed in forward direction? I am trying to add excess to it. So the reaction is in equilibrium. It is going to try and reduce it. How will it reduce? Only if it consumes it. And how will it consume it? If the reaction proceeds in the forward direction. So you may want to add these to your notes. To drive the reaction in the forward direction, that means in order to just bring about Mpv reduction, we use excess of the secondary alcohol. That means I'm talking about the reactant over here. And we remove the ketone from the reaction mixture as soon as it is formed. What is aluminium isopropoxide? I told you I'm going to break it down and make it very simple for you. Alcohol, remember, alcohol loses a proton and we get alkoxide. Yes, this is from the topic of alcohols. I've got propanol. So propanol means it loses a proton, so it will form propoxide. Yes. Now what if this is isopropanol? Yes, remember just now I mentioned iso, neo, everything covered. Yes. Now it is isopropanol. So it's going to lose a proton which is attached to oxygen, develops a negative charge. So this becomes isopropoxide. Right? Now this isopropoxide is combined with aluminium. Now look at the valency of this propoxide. It's 1. And what is the valency of our aluminium? Al3 positive. Remember? So that means one aluminium needs how many of these to balance itself? 3. So I'm going to put a 3 here, and there comes my aluminium along with it. Easy? This is aluminium isopropoxide. As simple as that, right? So if we break down our lessons into smaller things, it is easier for us to remember. Now go ahead, draw the flow chart and revise it till I come back with the next video on oxidation reactions of aldehydes and ketones. Take care and do share.